So if you are signing off on, let's say, a $500,000 5-axis machining center, I mean, the temptation to just check every single upgrade box on the spec sheet is incredibly strong.
Oh, absolutely. It's almost irresistible, then.
Yeah, exactly. Because when those capital expenditure budgets are finally approved, the default instinct for most shop owners and manufacturing engineers is to future-proof the floor.
You want to be ready for anything,
Right. So you buy the highest horsepower spindle, the fastest rapids, and almost always the absolute largest tool magazine available.
which seems totally logical on the surface.
It does. You figure, hey, a 120 tool matrix gives you the ultimate flexibility, right? Like it shields your production lines from whatever crazy complex geometries a client might throw at you next year.
But according to the highly technical engineering and manufacturing guide we're tearing into today,
Uh,
that specific instinct, maxing out your tool capacity, is routinely one of the most expensive, stealthy ROI killers in modern manufacturing.
Yeah, it's wild. And the guide we have today really frames tool magazine capacity as this critical, high-stakes operational decision rather than, just a simple feature upgrade on a brochure.
Exactly. We're looking at a document that strips away the marketing appeal of the quote-unquote everything machine. It really dissects the brutal mechanics of maximizing spindle uptime.
Which brings us to our mission for this deep dive. Today, we want to give you a strategic framework for evaluating hardware capabilities and specifically explore why excessive tool capacity fundamentally degrades machine efficiency.
And ideally, how to right-size your capital equipment without falling into that maximum capacity trap.
Right. Okay, let's unpack this because to understand why massive tool magazines can actually be detrimental, we first have to acknowledge the very real manufacturing bottlenecks that make them so appealing in the first place, right?
You have to understand the problem before you critique the solution.
Exactly. I mean, the drive toward high-capacity tool storage is really rooted in this desire to eliminate setup times and, well, human intervention entirely. Think of it like a chef in a kitchen.
Okay, a chef.
Yeah, if you have a massive tool magazine, it's like a chef having every single knife, whisk, and frying pan literally on their cutting board at once. They never, ever have to walk to the pantry.
Because walking to the pantry is dead time.
Right. Every time an operator has to power down the spindle to manually swap out roughing mills for a specialized set of finishing drills, that machine is just dead in the water. Manual tool changes kill factory efficiency.
And setup time is the absolute enemy of profitability. That's why a high-capacity magazine holding ball-end mills, form cutters, and, micro drills allows for continuous unmanned production.
The dream of lights-out manufacturing.
Precisely. You can load raw billets on Friday evening and walk into a pallet of finished components on Monday morning.
And beyond just keeping the spindle turning all weekend, there's a massive quality argument to be made for these large capacity setups, too.
The accuracy aspect.
Yeah, because when you have every necessary tool resident right there in the machine, you unlock one-stop machining. You never have to move the part.
Which is critical for things like aerospace housings or complex injection molds.
Exactly. You simply cannot afford the datum shifts that happen when you unfixture a part. Every time you unclamp a component, move it to a secondary machine, and indicate it back in, you are just stacking micro-tolerances.
You lose that true positional accuracy.
Right. Finishing the entire complex geometry in a single fixturing setup is really the only way to hold those tight tolerances across multiple features.
But what's fascinating here is the text highlights a really severe caveat to that pursuit of one-stop machining.
Oh, the speed issue.
Yeah. It warns that resident tool capacity is mathematically useless without corresponding tool chain speed.
Which makes sense. Capacity doesn't mean much if the machine takes forever to actually swap the tool.
Exactly. If your facility invests in this massive magazine, but the cam box driving the automatic tool changer is slow, you are merely shifting the bottleneck. You're moving it from a human operator delay to a mechanical delay.
You're paying to wait.
Right. For a large magazine to actually pencil out profitably, the source specifies you need a tool change speed of roughly 1 second to successfully compress that non-cutting time.
Wow, 1 second. That makes perfect sense. I mean, a slow tool change arm swapping tools 60 times a cycle is just going to hemorrhage cycle time.
It defeats the whole purpose.
But let's look at the core tension of the source material here. If we assume the tool changer is adequately fast, and a massive magazine guarantees this unmanned production and superior dimensional accuracy by eliminating refixturing.
Which are huge benefits.
Right. Then why does the text argue so aggressively against configuring machines with maximum tool capacity?
Well, the central thesis is that capital equipment configurations must strictly mirror your facility's actual current production portfolio.
Meaning you buy for what you're making today.
Exactly. The moment your equipment specifications outpace the geometric complexity of your average workpiece, you begin accumulating penalties. It's the concept of stranded asset value.
Stranded asset value.
Right. You are sinking capital into mechanical capability that just sits idle on the factory floor.
I have to challenge that premise, though, because in a dynamic job shop environment or even a pivoting OEM, production portfolios change,
How
right?
do you? Sure.
So shouldn't a business just future-proof their factory? Like if a facility buys a machine with a 60-tool magazine, but they only machine components requiring 12 tools today, they aren't really paying a penalty. They're buying an insurance policy.
An insurance policy.
Yeah, that unused capacity is just harmless, dormant space. It allows them to bid on higher complexity aerospace contracts next quarter without having to buy a whole new machine.
I hear that argument a lot, but calling it dormant space completely ignores the physical and operational realities of the machine architecture.
How so?
The source actually provides a complexity matrix to prevent exactly this kind of speculative buying. It offers specific, golden ratios for right-sizing your magazines.
Oh, the sizing chart. Let's go through that.
Yeah. So for simple 2.5D manufacturing, think basic brackets, cover plates, simple extrusions that only need a face mill, a few drills, and a tap.
Stuff that doesn't need a massive tool library.
Exactly. The strict recommendation there is a simple carousel or disc-type magazine holding 12 to 16 tools.
Which covers, frankly, the vast majority of standalone vertical machining centers doing basic job shop work.
Right. Then moving into medium complexity manufacturing, so typical aluminum housings or standard automotive castings.
The middle ground.
Yeah, the sweet spot shifts to 24 to 40 tools. This configuration hits the highest cost-performance ratio.
Because it gives you enough room to play with?
Exactly. You gain enough resident capacity to handle varied hole patterns and sister tooling for batch production, but you do it without absorbing the immense premium of high-end aerospace-level machinery.
Got it. And then the matrix scales up to the extreme end, right? The 60 to 120 tool chain magazines.
The behemoths.
Yeah, and the text clarifies these are explicitly designed for highly flexible manufacturing cells, or FMS. In those environments, you aren't using 120 tools on a single aerospace mold.
No, of course not.
You are utilizing a tombstone fixturing system where the machine might tackle 5 entirely different part numbers sequentially. Like you're storing tools for 5 different jogs at once.
Right. The resident capacity allows the CNC to jump from a titanium bracket program to an aluminum housing program instantly. It effectively drops the changeover time between completely different jobs to zero.
Which is incredible flexibility.
It is. But that is the only scenario where the ROI of a 120 tool magazine is justified. When you use that high-capacity magazine for simple 12-tool parts, those empty slots aren't just harmless insurance for next year.
Right.
They actively erode your profitability today.
And here's where it gets really interesting, because those empty tool slots actually physically penalize your cycle time.
Yes, the kinematics.
Exactly. When we look at total cost of ownership, we have to examine the kinematics of the machine. A small 12-tool disc magazine rotates its entire inventory in a fraction of a second. It's basically instant.
Because it's small and light.
But a 60 or 120 tool chain magazine takes up a massive physical footprint. It's a huge mechanical assembly carrying hundreds of pounds of steel tool holders.
The physics are unavoidable there. When the CNC calls for a new tool, the magazine has to accelerate that massive chain, index it across a long physical distance to find the correct pot, and then accurately decelerate it before the robotic arm can even make the swap.
It has a long way to travel.
Right. That extended travel path, plus the moment of inertia inherent in moving that much mass, wastes valuable seconds on every single tool change compared to a smaller, localized disc magazine.
And if you are running batch production of simple parts, those extra 2 or 3 seconds per tool change compound drastically.
They add up fast.
Yeah. Over a run of thousands of parts, your cycle times inflate entirely because your machine's physical architecture is just too large for the job. You buy the expensive upgrade to go faster, and the physical reality of the upgrade literally slows your production down.
And the penalty extends far beyond just kinematics. High-capacity magazines introduce this overwhelming software and data management burden on your operators.
Oh, tracking everything.
Right. In a 16-tool machine, managing tool life offsets is straightforward. But in a 120-tool matrix, Every single cutter degrades at a vastly different rate based on its material and time and cut.
Yeah, I mean, a half-inch carbide end mill roughing out steel might last, what, 40 minutes, while a small chamfer tool might last for weeks.
Exactly. The operator can't just load the chain and press the green button. They have to dive into the CNC's macro variables to establish complex sister tooling logic.
Which is practically a programming job in itself.
It is. They have to input specific tool life parameters, wear offsets, and cutter compensation data for over 100 different tools.
So, as the source points out, instead of cutting metal, your highly skilled operators waste their time managing a computer. They spend their shift acting as database managers.
Constantly updating offset registries and tracking the degradation of a massive inventory. It's exhausting.
And that software burden ties directly into what the guide presents as the most critical risk of overconfiguration, which is the maintenance domino effect.
The mechanical cascade.
Right. Because when you scale up from a simple umbrella tool changer to a 100 tool chain, you are exponentially multiplying the number of mechanical linkages, sensors, and fluid lines.
You're adding so many potential failure points.
Exactly. The physical reality of continuously moving hundreds of pounds of heavy metal tools means the system is literally constantly trying to tear itself apart.
And the guide systematically breaks down these failures to help you understand the stakes. It starts with mechanical degradation. A heavy chain, by its very nature, stretches over time under load.
It sags.
Yes. When a chain carrying dozens of heavy face mills and boring bars begins to sag even a fraction of a millimeter, the alignment goes completely out of tolerance.
And that alignment is critical, right? Because the tool changer arm operates completely blind.
It doesn't know where the tool actually is.
Right. It just assumes the tool is in the exact geometric center of the pocket. If the chain sags, or if a loose origin bolt ruins the tool numbering, the arm grabs the tool holder off-center.
Which is a nightmare.
It is. Over time, that slight misalignment wears down the mechanical gripper fingers. Eventually, it either drops a heavy tool directly onto the machine table, or worse, it misaligns the tool during the spindle clamp cycle and violently crashes the spindle taper.
And this mechanical wear is frequently accelerated by fluid and air system failures.
Oh, the hydraulics.
Yeah. Massive magazines require dedicated hydraulic systems to drive the tool unclamp pistons and rotate those heavy cam boxes. If the hydraulic oil experiences thermal breakdown or gets dirty, the shear forces destroy the internal pumps.
Low system pressure just stops the tool arm dead.
Exactly. But more critically, the text notes that as rubber hydraulic seals age and crack, they leak tramp oil directly into the machine's clean coolant reservoir.
Which completely ruins the coolant chemistry. That leaked hydraulic fluid basically floats on top of the water-soluble coolant and creates this oxygen barrier.
It breeds anaerobic bacteria.
Yeah. Suddenly your coolant smells like a swamp, it loses all its lubricity, and your tool life plummets.
It's a huge mess. And then you have the pneumatic issues. These machines are violently vibrating as they cut metal.
Naturally.
That vibration slowly backs out pneumatic fittings, causing invisible air pressure drops. And if the pneumatic pressure drops, the spindle can't fully release the tool, and the changer arm tries to rip a clamp tool right out of the machine.
It's just a terrifying cascade, and we haven't even talked about the electrical architecture.
Sensors?
Right. The CNC control relies entirely on proximity sensors and encoders to know the exact position of that massive chain. But the inside of a machining center is an incredibly hostile environment. It is filled with flying metallic chips and high-pressure coolant.
And inductive proximity sensors detect the presence of metal.
Exactly. So if a tiny microscopic sliver of steel or a dirty chip from the machining process lands on the sensor face, it sends a false positive to the PLC,
Sending bad signals to the control.
The machine control suddenly thinks the chain is in position when it's actually mid-rotation. The tool arm fires, smashes into the side of a tool holder, and just obliterates a mechanism that costs tens of thousands of dollars to replace.
And the human element just compounds every single one of these vulnerabilities. The guide specifically points out how daily operational mistakes lead to critical errors with these massive magazines.
Like what?
Well, operators routinely try to load customized boring bars or massive indexable cutters that exceed the strict weight limits of the changer arm.
Overweight tools.
Right. And that physically bends the cam mechanisms over time, literally breaking the gripper fingers.
Or, and this is a classic, Procurement departments try to shave costs by purchasing cheap aftermarket copy parts instead of original factory replacement.
And pull studs.
Exactly. A minor dimensional variation in a cheap aftermarket pull stud or tool holder clip throws the entire highly tuned high-speed transfer mechanism out of sequence.
It's just not worth the savings.
No. And to prevent these failures and maintain your target overall equipment effectiveness, or OEE, the daily preventative maintenance requirements are absolutely staggering.
Achieving that target OEE demands rigorous discipline. Maintenance teams must retension the heavy chains monthly to account for the stretch.
Monthly?
Yes, they must drain and replace the hydraulic fluids biannually to prevent that seal degradation and meticulously clean the microscopic gaps on every single proximity sensor quarterly.
Which takes a lot of time.
If a facility lacks the operational bandwidth to execute that level of strict, mandatory maintenance, investing in a high-capacity magazine guarantees chronic, unpredictable downtime.
So what does this all mean? When we aggregate the kinetic cycle time penalties of rotating massive chains, the exhaustive software management burden placed on the operators, and this terrifying cascade of mechanical and electrical failures we just covered,
Well, the underlying philosophy of this engineering guide becomes glaringly apparent.
the ultimate lesson is that you must ruthlessly match your machine's capacity to the exact geometric complexity of your parts.
You can't just guess.
No. Overspecifying your equipment under the guise of future-proofing is a financial fallacy. It doesn't actually future-proof your business. It simply buys you unnecessary mechanical complexity, inflates your total cost of ownership, and introduces a massive daily maintenance headache that actively saps your production efficiency. You have to know your needs.
You must evaluate your true production mix and exercise the discipline to procure, say, a 24-tool magazine when it is precisely what the process requires, and absolutely nothing more.
And that framework differentiating actual operational needs from the theoretical maximum capability constantly being marketed to us is a vital takeaway for anyone making capital investments.
It applies everywhere.
It really does. This exact same principle applies whether you are specifying factory robotics for assembly line, negotiating an enterprise software suite packed with modules your team will never actually deploy, or configuring server architecture for a new product launch. Excess capacity is never truly dormant. It always exacts a carrying cost.
It really challenges a pervasive modern mindset. We operate in a world that constantly sells us on infinite scalability and infinite upgrades.
Maximum potential at all times.
Exactly. Yet the data from this guide suggests that the ultimate competitive advantage isn't found in possessing the most features or the highest capacity. The real strategic advantage lies in having the courage to intentionally choose constraints.
Intentional constraints. I love that because unutilized capacity demands a toll in physical footprint, cognitive load, and relentless maintenance, which leaves you with a provocative thought worth examining today. How much of the daily maintenance in your own ecosystem, whether it is your business infrastructure, your departmental software subscriptions, or even your personal tech stack, is simply a hidden tax you are paying for capacity you never actually required?